Hi everyone, this is part 2 of my Unit 1 Essential Chemistry Skills video series. In part 2, we're going to talk scientific notation, we're going to talk accuracy versus precision, percent error, and scientific equation of a line. So sort of one topic and then 3 lab analysis, graphical analysis type concepts. As before, in the top left, you'll see the topic posted. So if you want to just quickly skim through the video to get to the part you really need the most, you can do so and know which the other parts for the other concepts here. So let's get into it with scientific notation. So if I were to ask you to estimate the mass of the Earth in kilograms, okay, how much would you think? You know, a kilogram is about 2.2 pounds. How many kilograms? A million, a billion, a trillion? Well, it's actually this many. Let's see, 597, that would be 1,000, million, billion, trillion, quadrillion, quintillion, hexillion, heptillion, perhaps, septillion, one of those two. It's a big number. Now, if we need to do any math with this, we would have to plug this number into our calculator. Very inconvenient. That's why we have scientific notation. It's also why we have metric prefixes, because you probably wouldn't refer to this in kilograms. You could refer to this in teragrams, exagrams, something larger. But probably more realistically, you would just use scientific notation. Scientific notation is just a different way of representing a number. So the way we put numbers into scientific notation is by starting at the very end and sweeping an imaginary decimal point until we end up between 1 and 9.99, or I should say, until we get to a number between 1 and 9.99. Now looking ahead over here, I'm going to sweep it from the right to the left, and I'm going to end it right there between the 5 and the 9. Because if I end it too soon and I end it here, it's going to be 59.7 times 10 to the something. If I go too far, it's going to be 0.597 times 10 to the something. Proper scientific notation has the front number between 1 and 9.99. So I'm going to stop it between the 5 and the 9. All right, so I'm just going to count the steps as I sweep it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, 5.97 times 10 to the 26th kilograms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 20. Yeah, I think I may have put an extra 0 or not enough zeros because I feel like when I Googled this, it wasn't 26. Don't quote me on this number, but this is proper scientific notation. Now, the way you write it in scientific notation should be consistent with how many sig figs are in the number. How many sig figs are in this massive, gigantic number? 3. Those trailing zeros do not count. And similarly, this number here has 3 sig figs. The front numbers only tell you the sig figs in scientific notation. Okay, let's talk about a small number. What if I ask for the radius of helium, which is the smallest element? You might say, hold on, isn't hydrogen smaller? Well, in terms of mass, yes. But in terms of volume, the actual three-dimensional shape, helium is actually smaller than hydrogen. You'll learn why later. So how small is this going to be in meters? Obviously a very small number. 0.1, no way. 0.01, no way. It's going to be 0.00000000031 meters. Again, this is why we have prefixes. This would generally be referred to as 31 picometers, or maybe 31,000 nanometers. Oh no, that's the wrong way with it. It would be 0.031 nanometers. Anyway, you can write this in scientific notation, or you could just use a different prefix. But if we did want to practice putting this in scientific notation, we're going to grab this decimal place, and again, we're going to sweep it until we end with a number between 1 and 9.99. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to stop right here because that gives me 3.1. If you went too far, 31, too big. Too soon, 0.31, too small. It's just right, like Goldilocks. 3.1 times 10 to the negative 11th. When I sweep it to the right and we have a decimal, it's 10 to the negative 11th power, which is the same as saying times 1 over 10 to the 11th. When you move it to the left and have a gigantic number, it's a positive exponent. All right, so that's how you put numbers into scientific notation. Let's practice taking numbers out of scientific notation. Wait, nope, let's practice putting these numbers into scientific notation. Okay, so you can pause it here and then unpause and we'll go through them. All right, 58,000, I'm gonna sweep it 1, 2, 3, 4 times and end it right here. 5.8 times 10 to the 4th. Over here on the right, I'm gonna grab this decimal point, 1, 2, 3, 4, 5, 6, 7. I'm gonna end it right there, 7 times. That gives me 3.20. Yes, I'm going to include that 0 because that 0 is a sig fig. These other zeros, these leading zeros are not sig figs. So 3.20 times 10 to the -7th. Yeah. This number with the 68. So sweeping it from this side, 1, 2, 3, 4, 5, 6, 7. 6.823 times 10 to the 7th. And you might say, do I need to include all those numbers, you know, the 6.823? Yes, because they're sig figs. Yes, you do. 0.007. Grab the decimal point. 1, 2, 3. Yes, I hesitated. But yes, I do want to move it 3 times because that gives me 7 times 10 to the -3rd. If you moved it if you stopped too soon, you would call it 0.7 times 10 to the -2nd, which mathematically is the same number, but it's not proper scientific notation. Every time you have scientific notation, your front number must be between 1 and 9.99999. So that being said, what if you have 10 billion of something and you want that in scientific notation? 1, 2, 3, 4, 5, 6, 7, 8. Now, do I go 9 and stop here, or do I go 10 and stop here? The answer is, oh, too far, sorry. I meant 10 and stop here. The answer is you go 10 and you, hold on, let me recount. I was looking away from the board. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to stop right there. Okay, which gives me 1 times 10 to the 10th. Notice there's no decimal place anywhere. All those zeros are not sig figs, so that's proper scientific notation with 1 sig fig. If I stop too soon, I would call it 10 times 10 to the 9th. Again, mathematically, these are the same. However, that's not proper scientific notation. It should be 1 times 10 to the 10th. Let's practice taking numbers out of scientific notation. So when I see a positive exponent, I know I'm going to be dealing with a gigantic number, which means I'm going to be adding zeros to the end and moving like to the right side, sort of sweeping to the right side. So I like to rewrite my number below, 5.92, and then I'm going to sweep it 9 times to the right to make this a giant number. 1, 2, 3, 4, 5, 6, 7, 8, 9. Fill in my zeros, 3, 4, 5, 6, 7 zeros. And then I'm going to rewrite this nice and clean without the decimal point at the end because the 3 sig figs here need to be represented. So 592, let's see, 0, 0, 0, 0, 0, 0, 0. Okay, so it's going to be 5, 920, 0, 0, 0, 0, 0, 0, 0. That's how I write that number. Let's go to the right. 3.82. So this one I'll write in place here. So I'm going to sweep it to the left 4 times to make it a teeny tiny decimal because it's -4. 1, 2, 3, 4. And I'll rewrite this nice and clean as 0 point. That 0 point is of course optional. I always prefer 0 point, but you can just write point. 0.000382. Got to include those 3 sig figs. Next one, I have 10 to the -7th. This is going to become a very small decimal. So I'm going to grab this decimal point and go 1, 2, 3, 4, 5, 6, 7 times. That's going to give me 0.000000800. And yes, I'm going to include those 2 trailing zeros because since there's a decimal place, they count and they're necessary to include. And finally, 2.1, I'm going to sweep it 1, 2, 3, 4, 5, 6 times to the right. And let's see, comma there, it's going to be 2,100,000. So you should be familiar with putting numbers into and taking them out of scientific notation. One last thing I'll say about this, please don't be intimidated by scientific notation. It's just a number. What you saw here originally in the black type, these are just numbers, okay? They're just numbers. Don't think of it as anything overly complex. If you want, you can take any number you see in scientific notation out of scientific notation before you work with it, okay? I see a lot of people that see it and just say, oh, I don't know what I'm doing. Yes, you do. It's just a number. The only other thing I wanted to cover here was working through calculations with scientific notation. I used to have my students work through the basics, like the stepwise process of adding, subtracting, multiplying, dividing numbers in scientific notation. That's unnecessary. We have calculators. You're never going to not be able to use your calculator for testing quizzes. So we don't need to go through the stepwise process. But I do think it's worth going through, actually plugging these into your calculator and getting the right answer. Because it sometimes will throw people off, especially with division. Now, there are really two ways of doing this. You can manually type in times 10 to the as part of your numbers, or you can use the E function. Now, if you use the E function, I'll show you, hopefully you can see it in the menu there. That top number would be 5.92 E6. Now, the E is going to be on this calculator. It's second, comma, which there's an EE right there. See there? It's 5.92 with a small capital E. The E means times 10 to the. So I'm just going to say 6. And right there, it stores that value. It actually put it into normal notation because it's small enough. So 5.92 E6. This other value, 8.27 E4, I can just multiply times 8.27 second, comma, 4. And my answer ends up being this, which is 4.89584 E11. E11 means times 10 to the 11th power. And you need to write it as times 10 to the 11th. Don't write it as E. But of course, we need units and sig figs. Let's look at units first. Meters times meters. The unit's going to be meters squared. And for sig figs, 3 sig figs here, 3 sig figs here. I need to round this to 3 sig figs. So looking at that number here, 4.895 is going to become 4.90 times 10 to the 11th meters squared. That's exactly how we're going to write that. Now, I typed that in using the E function, just to show the other way to do it. You can do this sort of manually by typing in 5.92 times 10 to the, there's a little caret button right there, 10 to the 6th. I like to hit equals now, let it store that value, okay? And then I'm going to say times, and it's going to say answer times 8.27 times 10 to the 4th equals. And I get my answer. Okay? So you shouldn't really run into any sort of problem when you're multiplying, whether you use one method or the other. But you can run into a problem when you divide, and we see it a lot. When you divide, it's very important that you either use the E function or you put the denominator in parentheses. And the reason for that is if you don't, and you type the whole thing as one giant step without parentheses, your calculator thinks in terms of PEMDAS. Where it's going to do all the multiplication and division together in the order you put it in. It's going to multiply 6.80 times 10 to the negative 5th. And then it's going to divide by 5.72. But then it's going to multiply by 10 to the 7th. It's going to multiply the entire thing by 10 to the 7th, as opposed to multiplying just the 5.72. So it's going to end up throwing your answer off by quite a lot. So let's practice both ways. I'll try with the E. So all I'm going to enter is 6.80 E negative 5. Hopefully that's coming through there. And I'm going to divide that by 5.72 E7. And there's my answer right there. Now, in terms of sig figs, I need 3 of them, and my unit is going to be kilograms per liter. So 1.19 times 10 to the negative 12 kilograms per liter. Okay. Now, I want to tell you one little tip here. When you multiply numbers in scientific notation, the exponents add together, and your answer will always be within 1 of the sum of those numbers. Now, why isn't it a perfect 10? Well, because technically, when you multiply these together, the front numbers multiply to give you something like, 5.92 times 8.27. That's going to be something like 50 or so. And since that's more than 10, it ticks your number up one. But the point is, you're always going to be within 1. So you see how when you added 6 and 10, you get times 10 to the 11th? It's within 1. So that means we're good. Okay, you know it's correct. Here, when you divide numbers, you're going to subtract those exponents. Negative 5 minus 7. What is negative 5 minus 7? It's negative 12. And notice how we hit it right on the nose there. The reason I bring this up is it's worth taking 10 seconds looking at what the exponents are and what they should end up being at the end of the problem, because then you can catch yourself if you make a mistake. How would you make a mistake? If you didn't use parentheses or E down here, you could end up with the wrong answer. Now, I believe my calculator automatically adjusts like when you say times 10 to the, but I know that our old calculators here, we use one of our room calculators, we can run into a problem. For example, if I say 6.80 times 10 to the negative 5th, and then I say divided by, I don't know if this is showing up on camera, 5.72 times 10 to the negative 7th, to positive 7th, times 10 to the 7th. And I hit equals, and notice the calculator gives me a final answer of 118.88. Is that correct? No, of course not. It's way, way, way off. Why did it do that? Because by not using parentheses or the E function, my calculator multiplied the entire thing by 10 to the 7th instead of dividing. So get around that by simply putting parentheses around the entire thing on the bottom or using the E function. Okay. Why don't you try these two on your own? You can pause and then we'll go through them. Okay, so for the top one, before I even work it out, what should my exponent end up being? Well, I have negative 3, and because we're multiplying these, we're going to add the exponents. Negative 3 plus negative 9. Negative 3 plus negative 9, same thing as saying negative 3 minus 9, which is negative 12. So I'm looking for negative 12 or negative 11 or negative 13. Just sticking that in my head for now. Okay, 1.2 times 10 to the negative 3rd. I'll do this one manually. Times 8.97 times 10 to the negative 9th. All right, now I have my answer here. Let's look at sig figs. I see 2 sig figs here and 3 sig figs here. So I need 2 sig figs. And my unit is going to be millimeters squared. So I have 1.0764 e negative 11. I'm going to call that 1.1 times 10 to the negative 11th millimeters squared. Am I within 1 of my target? Yes, I am. Negative 12, negative 11. I'm happy. Looking at the second one here, let's see what my target should be. 10 to the 14th divided by 10 to the 4th. You subtract the exponents. My target is 10. So I should end up either with 10 or with 11 or with 9. If you end up with something different, you definitely did something wrong. All right, I'll use E for this one. 5.029 E14. Again, that's what the E looks like. There are many E's in math. There's a lowercase e. Does not mean the same thing. Don't use it. Okay, so I hit enter just to store that. I'm going to divide this by 2.1892. E4. Enter. And I get my number here. My exponent is 10. Am I happy? Yeah, that's exactly what I thought it'd be. My unit. Meters cubed divided by meters squared. The answer is going to be just meters. This would be like a volume divided by an area. All right. So, and last thing, sig figs. I have 4 sig figs here, 5 sig figs here. I need 4 sig figs. So let's see, 2.297 times 10 to the 10th meters. There it is. Okay. If you can't get these answers, please talk to your teacher. It's very important that you work out how to put these into the calculator. They can be tricky. If not, once we start actually working with this stuff regularly, you're going to get all these questions wrong through, no real fault of you. It's just how you're putting them in the calculator. So talk to your teacher, make sure you understand how to put these in the calculator. Let's talk accuracy versus precision. This is a very simple one. One slide will cover it. When we look at data analysis, the data can be accurate, which is how close your data are to the correct or desired or target number. And yes, how close your data are. Data is a plural word. Technically, datum is the single. So yeah, accurate is how close you are to the correct or desired amount. Precision is how close repeated measurements are to one another. So it's like your consistency. So if you look at the targets down here, I think the text is probably cut off in the box, but if you hit the target, 8 times in a row, you are accurate because you hit the bullseye, and you're precise because your points all line up with each other. Look at the picture on the right. We are precise. You are consistent in your data, but you're not accurate because you didn't hit the desired target. So that's the difference. And a lot of times we'll compare accuracy and we'll compare precision. Percent error, another fairly simple concept. Percent error is a way of quantifying how accurate your results are, how close you are to the desired result. So here's the formula for percent error. It's your theoretical value minus your experimental value. However, since this is in absolute value here, the order doesn't actually matter in the numerator. It can be reversed, experimental minus theoretical. In fact, when I do percent error, I tend to just take the bigger one minus the smaller one just to keep it positive. But you can do either order. If it's negative, make it positive. But you do have to divide it by theoretical. Okay? You can't divide by experimental. This will give you a decimal times 100 makes it a percentage. Now, just for what these values mean, theoretical value is the correct answer or what you should have gotten. Experimental value is what you got when you ran the experiment. I tend to avoid using the word actual here because I've heard people say the actual answer is this one. You could kind of argue actual could be either. Like the actual value could be the theoretical value, like that you look up in a reference table, or you might say it in the context of what we actually got was this, which would be like experimental. So I tend to use theoretical and experimental. Your chem teacher might use some different terminology, but whatever you call it, this is our formula for percent error. Here's a sample problem. In the volume lab, a group gets a slope of 0.9228 milliliters per centimeter cubed. What is their percent error? Now, hopefully by this point in the year, you are familiar with the volume lab and what the desired slope is, which is exactly 1 because 1 milliliter equals 1 centimeter cubed. Hopefully I'm not spoiling that for anyone. So this right here, which value is that? Experimental or theoretical? That's the experimental value, because it's what they got in their experiment. What's the theoretical value? Exactly 1.00000. So percent error equals 1.0000 minus 0.9228. Now you can include the units in there, but they will end up canceling out when you divide by the same thing. Now, why did I choose to put 4 zeros after the 1? I didn't really have to, but it's to drive the point home that the relationship between milliliters and centimeters cubed is 1 to 1, but that's like a true by definition 1. It's completely true. It's a perfect infinite 1. It's not like sort of 1. So I don't want to just say 1 minus this, because as we learned in the last video, when you subtract or add numbers, you look at the places. And the number 1 is rounded to just the ones place, but this is an infinite 1. So we're going to go with all the decimal places here. Okay. Theoretical minus experimental divided by theoretical And again, the units are milliliter per centimeter cubed, milliliter per centimeter cubed, milliliter per centimeter cubed. They will end up canceling out. Percent error has no unit until you stick a percent sign on it, then it's just percent. Absolute value times 100. Okay, doing the math here. 1 minus 0.9228 equals, divided by 1 is really not even necessary, but just to see it. And I get 0.0772 times 100 gives me 7.72%. 7.72%. And we can say percent error for this. Now, in terms of sig figs, you do want to follow the rules. It is tricky though, because we're subtracting in the numerator and then dividing. We do want to look at the numerator to see how many decimal places will remain in our numerator answer and then divide when we do look at sig figs. So when I subtract those two numbers, I got 0.0772, and that is correct. 4 decimal places, 4 decimal places, 0.0772, 4 decimal places. Now I'm dividing 0.0772 by a perfect 1 with infinite sig figs. I have 3 sig figs divided by infinite sig figs. I should get 3 sig figs in my answer. So try to be consistent. Your teacher may be stricter or not stricter, kind of depending on what unit we're in or how far we've gotten about percent sig figs into percent error, but it's better to be correct by the rules. So you are subtracting, then dividing. So we should care about places and then sig figs. All right, one more. So a group calculates the density of a piece of gold to be 22.3 grams per milliliter. Very dense for comparison. That's like almost 3 times as dense as steel. Maybe more. I'm thinking steel's like 8 or 9 off the top of my head. I can't remember. They look it up online and find that gold's density is 19.3 grams per milliliter. What is their percent yield? So this one here is their experimental value. The correct one that they looked up is their theoretical value. The setup is one minus the other. Now for this one, I'm going to put their experimental first just to keep it positive. 22.3 minus 19.3. And again, you can put the unit, gram per milliliter. It will eventually cancel out though. We're going to divide that by the theoretical 19.3. So 22.3 minus 19.3 gives me 3.0 in the numerator, and I am going to write it this way to be consistent with sig figs. 3.0 in the numerator divided by 19.3 gives me 0.15544 and so on. 2 sig figs, because I'm now dividing, I'm going to call this 16%. Because again, in the numerator, I go with 1 decimal place, which gives me 3.0. Even though my calculator said 3, you should know that it's 3.0 because 1 decimal place. And then that gives me 2 sig figs. All right, that's percent error. Last topic of this video is scientific equation of a line. Now, hopefully you have some background in this. I'll go through it fairly quickly here. In fact, I'm going to cover this and go one at a time here. So what is the scientific equation of a line? It's Wilton chemistry's way of taking, or I should say Wilton science, because I know physical science does this as well. This is probably not something you're going to find in your chem textbook, though. It's probably not something you'll see at most other chemistry classes you take, like if you want to take college chem classes. This is something we really emphasize here at the high school. And it's about taking mathematical data. Like if you look here, the back of this, I have a couple graphs from Logger Pro. It's about taking the mathematical data here and putting it into science terms and science concepts. Because that's really what we want to do here. We want to take math and turn it into science related to the experiments that we run. So what that means is you're going to start with the equation of a line, which you should know by now is y equals mx plus b. These are all math terms. Let's put them into science terms. So you're going to look at the graph you just made from a lab, and you're going to replace y with whatever's on your y-axis, including the unit. You're going to replace m with your slope from the lab, including the unit. You're going to replace x with whatever's on your x-axis, including the unit. And then that leaves us with the y-intercept. And careful, Physical science students, this is something we do in chemistry that wasn't done in physical science. I believe in physical science, you just always include the y-intercept, but in chemistry, we're only going to include it sometimes. B is your y-intercept. If this is found to be negligible, meaning so small, it need not be considered, then it can be ignored and left out of our scientific equation of a line. Otherwise, you must write the value and the unit of your y-intercept. So how do we determine whether it's negligible or not, whether you can ignore it or not? The threshold we use in Wilton chemistry is 5%. If your y-intercept is within 5% of hitting 0,0, then we consider it so close to the origin, 0, 0, that we can ignore it. Now, when I say 5%, like 5% of what? Really, this means that your y-intercept is 5% of the maximum y value of your data. You know, if we want to kind of picture it, I don't know if it's going to work on camera here, but the idea is, are you within 5% of the origin? If you're less than 5%, then you're clearly so close that we can ignore that. But if you're more than 5%, you do have to include it. Mathematically, it looks like this. B is your y-intercept. Y max is the highest y value. Okay, so it's the y value of your highest point. If this is less than 5%, do not include the y-intercept. If it is more than 5%, you must include the y-intercept. Let's go through a couple examples because this is really tricky to just talk about without actually seeing it. So here's a quick, some sample data from the volume lab. How do I know it's a volume lab? Well, I see we have volume in milliliters on the y, volume in centimeters cubed on the x, and I can see that this is the linear fit for the cone. Okay, so the scientific equation of a line, we start with y equals mx plus b, and we're going to replace y, m, x, and maybe b, but definitely y, m, and x. So what do we do instead of y? We grab whatever's on the y-axis, which is volume in milliliters. That's your y, equals m is your slope. We grab that right from the data box. 0.9249 milliliter per centimeter cubed. That's m. I put it in parentheses because we're going to multiply this by x. X is whatever's on your x-axis. Now, you'll notice there's no numbers there. That's because when I cropped the screenshot, I accidentally forgot to include the numbers. So I just manually typed that in. But obviously, there were numbers down here. But that's volume in centimeters cubed. Volume in centimeters cubed. Okay, and we're going to pause here. So I consider these kind of the three easy ones. Y equals mx. Y equals mx. Now we need to think, do we include b or not? Here's what we do. B over y max. Absolute value times 100%. If that's more than 5%, then yes, we include it. If it's less than 5%, we do not include it. Okay, the b value is right here. It's always listed in your data table or your data box. In this case, it's 98.56 milliliters. The y max is not listed in that data box. You need to find it. And there's one of two ways. If the data are shown, which they are right here, then you just find the number and use that number. If the data are not shown, like it will on the next one, the data is not here, are not here, then you have to estimate it from the graph, okay? But if the data are available, use the data. Now, I see lots of numbers here. I need to grab the highest y value. How do I know which one of these is x and y? Well, it's right here, look. Volume in milliliters is your x value, sorry, your y value. So here's your milliliters. So it's out of these numbers. I hope that's coming up well on camera there, or on the Zoom. Yeah, so it's gonna be the 1430. You see that 1430 right there? Even though that's not the highest number in the data table, I see a 1506. The 1430 is the highest y value. That's what we're gonna use. 1430, and the unit there is milliliters. Okay, so 98.56 divided by 1430. 98.56 0.56 divided by 1430 gives me 0.0689. Okay, I'm going with 3 sig figs there because of the 1430. I multiply this by 100, and that gives me 6.89%. Now, what does that number really mean? See how my y-intercept, see how the line gets sort of close to the origin, but it doesn't quite hit it? It's off by 6.89%. Or in other words, this vertical distance right here from the y-intercept to the 0,0 origin is 6.89% of the height to our highest y value. That's what that really means. 6.89% means we're too far to ignore it. We have to include it. So my y-intercept right here is 98.56 milliliters. You add that on to the end. 98.56 milliliters. And that is your scientific equation of the line. Now you're not going to then do anything else with this. You're not going to like solve for anything. You're not going to plug anything in. If it just asks for the scientific equation of the line, there it is. Let's do one more. So here's another sample lab data, but this one says density of a metal sample. So notice what this group did. They took mass on the y-axis and volume on the x-axis, and they used that to find density. This is something that we'll be doing soon. Let's write the scientific equation of a line. So we start with y equals mx plus b. The y value is mass. I'm aware it says mass, grams, grams. That's just a typo there. So it's mass in grams equals m is slope 5.165 grams per milliliter. X volume in milliliters. Okay, so those are what I call the 3 easy ones. Y equals mx. You just write them as is. Now we pause before we do B. For B, we look at the y-intercept. It's right here, 5.796. That's the y-intercept. We divide that by the y-max. What's the y-max? Uh-oh, I don't see the point anywhere, or I don't see the data numbers. So we're going to have to estimate it. Now, it looks like I wrote over the top of this. Let me see if I can move this. Yeah. So you want to look for the actual points. They're kind of hard to see, but it's these red circles. I got 1, 2, 3, and the last one's actually way up here. You can almost only see half of it. But if we judge that to be the highest point, you're going to trace it over to the side and estimate it as best you can. So it ends somewhere over there. Now looking at the side, I see lines for 150 and 200. I see lines in between them. Those are tens. So you're going to go one better. Remember from the last video? You're going to go to the ones place. So I'm going to judge this to be like 218, something like that. Okay. 5.796 divided by 218 gives me 0.0266 with 3 sig figs. That becomes 2.66%. What that means is we are only 2.66% away from the origin. And if you look at this graph compared to the last graph, well, I wrote all over this one, but you can see how this one is really close to the origin. It's so close that we can ignore the y-intercept. It's less than 5%. So all that means is we leave it out and we are done. And that's your scientific equation of the line. Okay, that's it for this one. Be sure to talk to your teacher if you have any further questions, and I'll film the next one at some point soon.